Okay, this video I'm going to go through flux surface perturbations. So I'm going to start by looking at what happens when you have a nested set of flux surfaces, like in a tokamak, and then you make a perturbation to them. So you either some external force or some internal instability leads to a change in the shape of the flux surface. And so we can derive an equation called the cylindrical tearing mode equation, which describes how the current in the plasma is driven, or how current changes when we change the surface of the flux surfaces. And this leads to the idea of resonance surfaces, either inside or outside the plasma. And this will be useful for understanding kink modes and tearing modes later. So we're going to start with a large aspect ratio. So this means that in a tokamak we are using R is much bigger than, so big R is much bigger than little r. Often this is written as an inverse aspect ratio, which is the minor radius to the major radius. And we assume that this is a small number. This is the inverse aspect ratio. And so what we're basically looking at here is a cylinder. So we have a cylindrical plasma. So we've straightened out the tokamak into a cylinder. This is the minor radius here. The major radius, this will be bent around in a circle. But we have magnetic field, which is twisting around here. So this is the B field, right here. So this is B, like this. And so it has a poloidal component and a toroidal component. And now in the cross section here, we can draw this as a cross section like this. And this has a set of nested flux surfaces like this. And so here we have the poloidal field, so B theta. And we write this in terms of a flux. So we write that B has various components. So we write that BR, for example, in the radial direction. And so what we're going to do now is we're going to look at the flux surfaces, and we're going to make a small change to them. So we're going to imagine there's a change in the flux psi. So perhaps we push some parts of the plasma out, some parts go in. Make some kind of change like this. So we get a small change in psi, which results in a twisting or a change in the shape of the plasma. So here, this example, this would be an m equals 3. This example, so I have 3 periods in the poloidal direction. We're going to consider m equals 1, for example, which is just a shift. M equals 2, which would be like a flattening. And then, of course, you can have higher modes as well. And so we have a change in the flux. So we hold delta psi is the change in flux. And so we can write down the changes in the magnetic field. So this is just the change in the magnetic flux. And then from this we can work out what the currents are. And so because we have that J, for example, so J in the toroidal direction is just 1 over mu naught times the toroidal component of curl of B. So that's basically curl of the poloidal field, again in the toroidal direction. And so from this we can just write down that essentially J phi, it's just the second derivative of psi, delta psi. So it's the change in the toroidal current density. Okay, so far this is pretty general. So we start with some flux, we make a small change to it, and this gives us a changed magnetic field, and so a changed toroidal current. What we can do now is we're going to assume a particular form of this change. So we're going to assume that the perturbation to psi, which in general depends on r and theta and phi, is just some function of radius times a Fourier series. So we just decompose it in terms of poloidal mode number m, which is this I drew up here in this equation here. This was m equals 3. And then also have a toroidal mode number n. And here we could define phi. So phi here is a toroidal angle for tokamaks. For a cylinder, we can define basically phi is just the z direction divided by the major radius, and r naught here is a constant large major radius. And so here we just define an angle in terms of a distance z along here. And so we can write this in the form, this will eventually translate into a tokamak, so n would be the toroidal mode number, and m would be the poloidal mode number. Okay, and then what we can do is we can assume we have a slow perturbation, so either close to marginal stability or at least slow compared to the fast magnetosonic waves. And what this means is that in this case we have basically force balance is obeyed at all times, because the difference between the forces, so difference between J cos P and difference between that and grad P, is what's accelerating the plasma. And if the acceleration is slow, then these forces are very large compared to the difference. And so we can just assume that these are equal. And so what we can do is take the curl of this equation, and the motivation for doing that is that curl of the gradient is identically 0. And so this gets rid of anything to do with pressure. And so we just have the curl of J cos B is always equal to 0. And then we can put in the perturbation. So we can look at when we perturb this, what happens. And if you just remember the first order linear perturbations, so we have a delta J and a B naught, and a J naught and a delta B. And so we end up with, so we just use a vector identity to expand this out. So that gives us all these terms. And then many of them will disappear. So for example, divergence of B is of course 0. And divergence of J is also 0 because there's no charge build up in the plasma. So these are all 0, as is the perturbation to J, so we divergence free. And then we have some other effects we can bring in. So for example, this one here we have a gradient of equilibrium magnetic field, and this is very small compared to say the perturbation of the magnetic field. And so here this gradient is small. Because the equilibrium magnetic field is large scale, slowly varying, or assume that the fluctuation is localized, quite small, and so this gradient is small because the magnetic field is slowly varying. You could ask why this is not necessarily small. This is because the current can be quite localized, the equilibrium current, even if the magnetic field is quite large. You can think about a current in a wire, for example. Outside a wire, the magnetic field is slowly varying, and it travels long distance, but the current is very localized, so it's just inside the wire. And so here we're safe to neglect this term, but not this term. And so we're left with just three terms in the end. So I have these three here. And then we're going to take the toroidal component, and that will remove this last term here. Because the toroidal field the perturbation is mainly in the poloidal plane. So here we've made a perturbation to psi, which is in the poloidal plane. So we're disturbing it like this. There will of course be some change in magnetic field in the toroidal direction, but because the equilibrium field is much stronger in this way compared to the poloidal field, and the structures will therefore be very long in the toroidal direction compared to the poloidal direction, we can neglect the toroidal magnetic field perturbation. And so we're just left with these two here. So I'll start with this component. For example, this is the perturbed magnetic field and the derivative of the toroidal current. So in a large aspect ratio, so i.e. this is where R over R naught over R is bigger than 1. What we have is that the J toroidal current is only dependent really on radius. So it doesn't depend on the poloidal angle. In a torus, when you bend, in a finite torus, when you bend this around into a torus, the current will be different on the inboard side and the outboard side. but in large aspect ratio it becomes only a function of r. And so this term is basically only, this gradient is only in radius. So this is like the delta b r times dj phi by dr. And then if we put in the expression for delta br from above. So then the next thing is to take this part here, and this one, this is quite a useful expression. So we're going to take the equilibrium magnetic field dotted with the gradient, and so this is the derivative along the magnetic field. So we just write that the B naught has two components. So it's the poloidal field in the poloidal direction, and then plus the toroidal field in the toroidal direction. And now in angles, the gradient, well, you have a d by dr, for example, which is in the r direction, and then you have a minor radius derivative, so d by d theta. That's in the theta direction, and then very similar in the toroidal directions. This is the major radius. And so here what we're going to do is just take the dot product b naught dot grad operating on delta j, and this is just delta j times theta, delta j in the toroidal direction. And then we can use the derivatives in theta and derivatives in phi. We can just substitute in the expression for the variation we're putting in. So we're putting in a delta phi, delta psi here. The flux has this form, and so when you take a derivative in theta, you get I in m, and we get derivative in phi, you get a factor of I minus I times n. And so this whole thing just becomes simplified, so we can turn these derivatives into multiplications by I m or I n. Okay, then we're going to put these together. So we're going to have this term here with the delta j, and we have this term here, and the sum of these two is equal to 0. So we're going to move this over to the right hand side, and we can also make a simplification. So we can make this again has a d by d theta. So this just ends up being an I m and then a delta psi, and so this simplifies things as well. And so we just put this on the right hand side and this on the left hand side, and so we just have, and then from this we can make some useful substitutions. So what we have here, we can use, for example, in here we can use the substitution that q, the safety factor, is b phi, that's minor radius, over b toroidal times major radius, and this is the safety factor. So it's the number of times a field line goes around toroidally for each poloidal turn, and so we can use this to replace this b phi over r naught. Just replace this in here with a q b theta over r. And so what we end up with, that means that b theta over r is in common with both and can come outside. And then we can just rearrange, cancel out some terms here. So m over r on both sides, of course, cancel out. We can move this over. You can write this in terms of this is just 1 over mu naught, then delta squared delta psi. Always leave it as j phi. And so we end up with delta j phi. On the right hand side, and this is the cylindrical tearing mode equation, and so it tells us how the perturbed current depends on the perturbation of the psi and the equilibrium current density. And so there are some interesting features of this. Probably the most important is where what happens when this goes to 0. So when q is equal to m over n, what happens is this goes to 0, and so either the perturbed flux must go to 0, or the current becomes essentially infinite, and so you have singularity in the perturbed current, and this corresponds to a case where the perturbation matches the field line pitch, and so you have a perturbed flux surface. So what's happening when you have when Q is equal to m over n is if you have a perturbed flux surface, so here the green is an m equals 2, and then this perturbation is twisting around. So I've tried to draw it so it's kind of vertical here, then twists sideways here, and then back to vertical there. If the pitch of this perturbation follows the field lines, so if the magnetic field is also following the same pitch, then this is resonance, a resonant condition. And so what happens is that some field lines are being pushed out, some field lines are being pushed in, and there's no bending of those field lines. They're just moving outwards or moving inwards. And this is a resonance. So this is often a condition where instabilities will occur because it minimizes the field line bending. But what we see here is that in this case, if you have a perturbed flux surfaces, you end up with an infinite current density at those surfaces. And so if you have the typical profile of the magnetic surface, so you have like a radius, and this is Q. What will happen in a cylinder is so the Q surface, something like this, for example. And if you have an external perturbation, so we apply some external coils to put in a perturbation. So we put some external perturbation delta psi. This delta psi will generally decay inwards, and it will until it reaches its surface, where some surface here where Q equals m over n. And in ideal MHD, that will drive a current on that surface, so it's an infinitely thin but infinitely large current sheet, and that will suppress the perturbation. So delta psi will go to 0 at that location, and the plasma will screen out the perturbation. So anything inside will be no perturbation, and outside you'll get perturbation. In a tokamak, this is a little bit different, because in a tokamak, the curvature of the bending around in a torus means that the different mode numbers m and n are not good quantum numbers. So m modes couple together, and so you can end up with modes on the inside like this. So if you apply an external RMP, for example, you find that the modes are that mode is suppressed on its resonant flux surface, but then there are some modes used. So you still have some finite amplitude inside, but this is quite a common thing seen, that you suppress perturbations on the resonant surface. And for instabilities, this has some useful consequences. So often instabilities which are kink instabilities or ideal instabilities occur so that this surface is outside the plasma. So if you have I'll draw the Q profile. So if the plasma edge is here, this is the plasma, and there's a vacuum in here, what can happen is you have instabilities which are resonant just outside the edge of the plasma. So this is Q equals m over n. And this can happen without driving large current sheets in the plasma. And so kink kind of instabilities, so kink or peeling. So kind of peeling modes tend to occur where this Q is just slightly outside the edge of the plasma. This makes them very sensitive to exactly what this Q is, because if the safety factor changes a little bit, this surface will move inside the plasma, and then it will be stabilizing, because otherwise it would have to drive a very large current sheet. And then there are instabilities where the surface is inside the plasma, and these are called tearing modes, which we'll cover in a future lecture. Okay, thank you.